Good morning.
Any questions?
Yeah. So on the last problem on the master set, it was a ball or a box going down a ramp, like just going down a ramp and then hitting another box into a spring.
Right.
Can you just do something similar to that?
Good. Do they stick together? Or perfectly elastic?
Let me look. Wait. Yeah, perfectly elastic.
Okay. Did he give you the height or the angle?
They give you the height. I think, well, they also gave you the length of like the ramp. Does that, how does that help?
That helps in there was one of the questions was how far back up the ramp does it go?
Okay.
So that's where it helps. All right. So the first part where it's sliding down the ramp, that's a conservation of energy problem. So I assume everything's frictionless. Well, E initial equals E final. I'm going to change the subscripts here. We're going to call this 0, 1. And then 2 is after the collision. So E0 equals E1. And I have only 2 types of energy I'm dealing with, so potential and kinetic. The third type, rest energy, would only come into play if it bursts into flames or somehow combusted. So first part, because in order to figure out what's going to happen to this, we need to know how fast this one is going when it hits it. So we have this set up here of, I put final, it suddenly changed midstream here, H1. All right. So what can we set equal to 0? Or what is equal to 0?
The mass. Can we cancel out the mass?
We can. Not because it's 0.
Well, yeah.
Okay?
Can we cancel the initial or the final or the initial velocity for box 2? Because it's just not moving.
Box. There's only one box in this problem. We're dealing with this going from here to here. But I didn't state it. My remembrance was that the start's close enough to rest.
Yeah, like just so it's just before it starts moving.
Okay. So therefore, that's got to be 0.
Yeah.
Because of the problem. Final speed, the speed when box gets down to here, it's not going to be 0 unless there's friction. So that leaves us with the heights. So what are the heights equal to 0?
If we set 0 at where the rest of the thing is, yeah.
Down here?
That would be
okay. And I appreciate the wording that if we set it. So yes, indeed, let's go ahead and set h is equal to 0 here. So therefore, that is 0, because Jack says so. And we're just left with acceleration due to gravity times the initial height is equal to 1/2 times the speed squared at 0.1. And so V1 is equal to the square root of 2G H sub 0. So now it's a plug and chug. Now, also note this is the speed. Now we know from context that the direction is going to be to the right. So the square root of 2, do I specify? I assume it takes place on Earth?
No.
Well, I'm going to put this on Earth too, just for ease. So 10 times 15. No, that's not right. 17 points. The answer is $3.2.
Yeah, usually.
Yeah. That's what I got.
All right. So that's the energy bit, and then we have the collision, perfectly elastic collision. So what are the two criteria for perfectly elastic collisions?
Energy is conserved.
More specifically,
Kinetic.
Good.
yes. All right, so we got kinetic conserved and
they bounce off of each other? Right, elastic they stick together. No.
Momentum.
Yes. That's the other one. So now we have the three methods, of which it doesn't matter which one you pick. It depends on the way your brain is functioning at that moment and which one you've actually practiced ahead of time. So, any particular care about which method we pick?
2.
2? 3. Too late. All right, so method 2. So basically the problem is I got a 3 kilogram mass heading to the right at 17.32 meters per second. And it's going to hit an 8 kilogram mass starting at rest.
What was the... Did we just make that up? The 17.32?
No, that's what we just got.
Okay.
Unless some of you were lying to me, the answer is really not 17.32.
No, it is. It is.
So this is before the perfectly elastic collision, and then after. I'm betting the 3 kilogram mass is going to bounce backwards, and the 8 kilogram mass will be heading to the right.
Now, you've done that just like from logical thinking.
Yes.
But the reason why we just put the two objects just in a straight line and just saying they are going to collide, because isn't that because we don't care about just what's going on in between? Like, as long as there's a collision, we just care about the end result.
Right. As long as there's no, like when it gets, as long as there's no friction along here,
Right.
then up and even hitting this, then whatever the speed at the bottom here is has to be the speed when it hits. Did that answer your question?
Yes.
Okay. Other questions before we do method 2? All right. I'm hoping these are not the same numbers that are in the problem.
They are.
Okay. All right, so method 2, we've got momentum. So I've got 3 times 17.32, basically square root of 300, plus 8 times 0 is equal to 3c plus 8d. We're seeing near the final velocities. Then I've got 17.32. So method 2, the second equation, comes from combining the conservation of kinetic energy and momentum, and we end up with 17.32 minus 0 is equal to d minus c.
Worth having times 3.
This is the relative speed of approach equals relative speed of recession.
Got it.
And since I did the velocity of the 3 kilogram first, in the left-hand side of the equation, I do the velocity of the other one first, the other side. So now it's 2 equations, 2 unknowns. It's an algebra problem, of which there are many methods to choose, but I'll go ahead and substitution. So D equals C plus 17.32. Pop that into there. That is something 51.96 equals plus 0 equals 3C plus 8 C plus 17.32.
Right on the money, Dr. Fox. 51.96.
Some mornings, it works. All right. Distributing.
I got 138.56.
Okay.
That's what you wrote.
Yeah, that's a 1-3 there, not a D. All right. So we end up with a brand new color just to make it exciting and bold. So I have 51.96 equals 11C plus 138.56. I'm trying to isolate C, so I need to get rid of all the ne'er-do-wells and hanger-ons. So first we get rid of this. We're basically doing the reverse order of operations. And so I'm left with 11C on the right-hand side, and on the left-hand side, a negative number, which is what I would expect.
I got negative 86.6.
5.6. Sorry, what you getting?
Negative 86.6.
Oh, doubled up the negative there. And that's a 6 there. My handwriting's getting worse. All right. And so now the last thing hanging on to C is the 11, and so we undo it by dividing.
I got negative 7.872 repeating.
The 872 repeats?
Yeah, the 872, 72727.
Oh, just the 72.
Yeah.
Units?
Meters per second.
All right, so we have the velocity of the 3 kilogram mass after the collision. We can then just plug into this equation right here to find D. And so if we add 17.32 to that, we get 9 point something.
No, what did we say? 86 point. Oh yeah. Okay.
Wait, 47?
45.
45.
I excluded some of the repeating numbers.
All right, meters per second. So this tells us that the 3 kilogram mass is indeed going to be going in the negative direction, which we didn't explicitly define, but when we wrote 17.32 here, we defined the positive direction to be to the right, as given the reference to the diagram. Let's make it explicit. So the negative answer here for the final velocity of the 3 kilogram mass, negative, so it is bouncing back towards the ramp, and the other one heading to the spring. Now there was a 251 problem. This was had something very similar to this. This goes bouncing back, the other one hits the spring, compresses it, and then they're going to collide again. And so I asked them the question, at what time do they collide again? That was one that, as I was working it out during the test, I realized was solvable, but a whole lot more complicated than I had originally expected. That's what happens when I don't prove.
Did anybody get it right?
I had one student get really close, I mean, one careless error, but she was a phenomenal student. And was going to do anything except become a physicist. Her mom was a physicist. Right, I assume that the comment?
No, it said her mom was probably doing all her homework.
Her mom unfortunately had passed by then. That was sort of a sad ending there.
Yeah, I wasn't ready for that.
Let's bring it back up and talk about physics. So, was the question this far, or how far the spring compresses? I don't know how far you wanted to take it.
I think this is fine.
Okay.
Where does the spring come into play?
Afterwards, the original problem, this came down, hit this hits the spring, and then how far will the spring compress, and how far will that go back up the ramp?
You're talking about 3 kilogram mass?
Yeah, 3 kilogram mass after the collision is going this way, and the question is how far up the ramp does it go?
How'd you find that?
Well, you know how fast it's going, so
Right.
it's a conservation of energy thing again,
Oh, okay, I got you.
just in reverse. And then there's the subtlety of the language. It's not how high does it go, it's how far up the ramp does it go.
So you have to find the slope.
Well, you've got, in the original problem I gave this and that, so you can figure out that angle, and then, because what the energy is going to tell you is how high up it goes, and you basically find the hypotenuse. And if you've already done it, and did not catch that subtlety, it's a minor reduction.
Yeah, home really late last night. I want to get the master set in tonight.
Look forward to weeping tears of joy.
Yes. It might just be tears, but let's keep our hopes up.
Sometimes we need to just let it out. Other questions? Or was there a question that I was in the middle of answering and then forgot? All right. By popular demand, rotational stuff. All right, what we're going to do is we're going to do some legal betting here. We're going to see if physics by democracy works. And I will say from experience, it works about half the time.